For today's video, you are going to need your reference tables and your calculator because we will be doing some calculations. So we know that light is made up of electromagnetic radiation, and those light waves have a specific energy and frequency. If you've already taken physics, you will be very familiar with those concepts. Even without physics, you'll remember from your previous science classes learning about electromagnetic radiation and where the different types of waves fit in on the electromagnetic spectrum. So we have the visible spectrum that makes up a very small part here, and then different colors have a different wavelength, different energy, different frequency. Higher energy than the visible spectrum would be UV, X-rays, and gamma rays would be the highest energy. Lower energy than visible would be infrared, microwaves, radio waves, and non-radio waves. You will remember from physics or even junior high science talking some about waves and the different parts of the wave. So our wavelength is the distance between two repeating points. So it could be from the top of the wave to the top of the wave. It could be from the bottom to the bottom. The amplitude is the highest point, so that would be there. As the frequency increases, the wavelength will decrease. So the frequency, which is abbreviated with F, or they'll use nu, which kind of looks like a V in this font, even though it's a Greek letter. Frequency is the number of waves that pass a given point in a second. So the unit is going to be per second, meaning if it's 35 per second, you have 35 waves per second that pass that point, or hertz. So again, if we have a higher frequency, you have a shorter wavelength. Lower frequency, longer wavelength. On your reference table, you want to look at the atomic structure section, and we have a formula that we are going to use. So it's C equals wavelength times frequency. Again, that's the Greek letter nu, or you can just use F that you did in physics for frequency. So this formula is on the reference table. C is the speed of light, which is 2.998 times 10 to the 8th meters per second. And then you'll have wavelength. And these are defined on the reference table. And F, or nu, is frequency. So if we think about that last slide that you just looked at, when you have a higher frequency, you have a smaller wavelength. So they are next to each other in the equation, which means that as one increases, the other one decreases. So they have an inverse relationship. So that's an important thing to make a note of, that wavelength and frequency are inversely proportional to each other, meaning if one of them is higher, the other one will be lower. So if you have a longer wavelength, you will have less frequency. Less waves will go by per second. A shorter wavelength, you will have a greater frequency. More waves will go by per second. So wavelength and frequency are inversely proportional to each other. All right, if you do not have your reference table and calculator handy, grab those because we are going to need them to do these two calculations. First calculation, we're looking for the wavelength of light that has a frequency of 5.89 times 10 to the fifth hertz. So we are going to use the formula from the reference table. C, speed of light, is equal to wavelength times frequency. So our speed of light is 2.998 times 10 to the eighth meters per second. We are looking for the wavelength and we have the frequency. Now remember, hertz is the same thing as per second. So you can do per second or second to the -1. All right, so we plug that all into our calculator. 2.998 times 10 to the eighth divided by 5.89 times 10 to the fifth. And that gives us a wavelength of 509 meters. So that would be one long wave. All right, in our next one, we are looking for the frequency of blue light if that blue light has a wavelength of 485 nanometers. All right, so we're going to use the exact same equation, but hopefully you are noticing that our speed of light is in meters per second. So we are going to have to convert to the nanometers first. So 485 nanometers, 1 nanometer is 10 to the -9th. So it's 1 billionth of a meter. So we can plug it in just like that. So we'll take our speed of light, now I'll do meters per second, is equal to 484 times 10 to the -9th meters. Now I realize that that is not proper scientific notation, but it is not my final answer, so it's not worth converting it. So again, that's because 1 nanometer is 10 to the -9th meter, so 1 billionth of a meter. So we just multiply by 10 to the -9th, and then we solve for the frequency. Once we plug that into our calculators, we get 6.19 times 10 to the 14th per second or hertz. So what that means is we get 6.19 times 10 to the 14th waves traveling through there per second. So that wavelength is very short because it's in nanometers, so therefore my frequency is very high. We can also calculate the energy of a wave. So we're going to use this formula that is on our reference table. And it's E is equal to H. H is Planck's constant. The value is given on your reference table times frequency. So even if we have wavelength, you can get from wavelength to frequency and then to energy. Just like our other formula, this formula is on the reference table, so we do not need to memorize it. One of the ways that we'll be using this formula is for a given wave. If we know, say, its wavelength, we could calculate its energy, and then we would know where that would land on the electromagnetic spectrum. So would it be visible light? Would it be UV radiation, or so on? Just like with our other ones, we do need to know our relationships. So if we have a greater frequency, that will correlate with a higher energy. And if we have a longer wavelength, that correlates with a lower frequency. So it's very good to know those relationships. So you can visualize your wave. You also can use the equation to help you out. So we know mathematically if our frequency is higher, that will correlate to a higher energy. If our frequency is lower, it would give us a lower energy. All right, so blue light has a wavelength of about 470 nanometers. So the previous question had used 484 nanometers for blue light. Those are very similar. So blue, there's different shades of blue, hence the difference there. So blue light has a wavelength of about 470 nanometers. Calculate the energy of a photon of blue light. So first thing we have to do is convert nanometers to meters. So we will do 470 times 10 to the negative ninth meters. We will plug that into our first formula. So the speed of light is equal to the wavelength times the frequency. Once we get that, once we find the frequency, then we will solve it or put it into our next formula. E is equal to h, which is Planck's constant, times the frequency. So it will be a two-step problem. So first we take the speed of light and we plug in our wavelength in meters so that our units will cancel. We solve for frequency. So let's put it down here. So we get 6.38. Actually, it would be, 6.38 times 10 to the 14th hertz or per second. Okay, then once we have that, then we can plug into our energy equation. So energy is equal to H, which is Planck's constant, which is on our reference table 6.626 times 10 to the negative 34th joule seconds. Then we multiply by the frequency that we just found. Notice that is per second, so my seconds will cancel out, leaving me with joules. Once we plug that into our calculator, we get 4.2 times 10 to the negative 19th joules. So we don't have a huge amount of energy with that, which makes sense because it is just visible light. It's not gamma rays, x-rays, so it makes sense that it would be not a huge amount, and that is just per one individual photon of light. Now, alternately, you could have taken these two equations and merged them into one and done it in one step, and that would be perfectly fine also. All right, in number 2, we are going to be calculating the frequency of a photon that has the energy of 3.7 times 10 to the negative 19th. So we're going to use our energy is equal to Planck's constant times frequency. We have the energy, 3.7 times 10 to the negative 19th joules. Planck's constant on your reference table, 6.626 times 10 to the negative 34th joule seconds. And then we look for frequency. So we just input that into our calculator and we get 5.6 times 10 to the 14th per second or hertz, meaning you get 5.6 times 10 to the 14th waves passing by per second.